This is overview of natural language processing. What is natural language processing? Natural language processing is a subfield of artificial intelligence. It is closely related not only to AI but also to computer science, the science of human language as well. Natural language processing also is based on machine learning methods, as we can see from this diagram. Also, of course, it has very close relation to deep learning. So, typical examples of natural language processing include machine translation, like Google Translate, DeepL, etc., speech recognition systems, also very popular now, chatbots and conversational artificial intelligence like ChatGPT, Gemini, DeepSeek, etc. Such applications as sentiment analysis of the text, text summarization, question answering, and many more. So, the earlier approaches, even from the 1950s of previous century, they included basically rule-based systems, which included some rules based on linguistics, grammar. But modern approaches, they use basically statistical methods and especially machine learning, and of course deep learning. And now very popular are so-called large language models, LLMs. These are machine learning models which are trained on massive text data, on the gigabytes or even terabytes of data, due to which these models can learn structure, meaning, and context of human language. What is the idea, very simple idea behind language modeling? It is deceptively simple. It's next word prediction. The core idea is to predict the most likely next word given a sentence. For example, if we have a sentence, the capital or beginning of sentence, the capital of France is, well, the model should give answer Paris, or maybe some variants with different probabilities. So these models are expected to learn grammar, facts, logic, and style. How this text generation is working. For example, we have the beginning of sentence, the capital of France is, then the model computes probabilities for the next word. For example, in this case, Paris is 85%, London 5%, Berlin 3%, etc. So, or maybe some there could be some paradoxical answer. For example, the capital of France is Madrid, which is wrong, for example, would be continuation. But nevertheless, the large language model should give a list of probabilities for the next word and select one of them. Which of this list word will be selected depends on so-called temperature. Temperature, if we have a low temperature of our algorithm, that the text will be generated text will be quite predictable. It means that the most probable word will always be selected. But when temperature is high, possibilities for other words to be included into the answer are given. So once we have generated the next word, then we go again to the first step. We again the next word after the sentence given one more word, etc. So in this cyclic nature, this large language model, it generates text. Returning to this example, the capital of France is, yes, if we have probabilities given by so-called softmax algorithm, for example, Paris is 85%, London 5%, but if we increase the temperature of our algorithm, then the probabilities become quite smooth, and for the first side, wrong answers are also given chance. So increasing temperature usually is used to enhance the originality, not originality, but creativity, some new inventions, some new styles, some new phraseologisms. They can be included into the text to express the initial idea. Okay, so let us consider how NLP works, like how NLP or LLM, large language models, how do they work? They follow quite typical, as for these days, workflow. First, we have tokenization. Tokenization means splitting our text into small parts. very soon we will see how it looks, what are the methods. Then we make some pre-processing of our text normalization. We convert it to lowercase. We exclude some maybe punctuation marks. So then very important stage, embedding or vectorization, where each word or part of the word is mapped into a vector. Then we make context encoding. So the different vectors, they corresponding to the parts of the sentence, they exchange the information among each other to reveal the context of the intercommunication between different parts of the sentence. Then we have finally decoding, generation, and final text processing to present the resulting text depending on task to the end user. So let's start with tokenization. Tokenization can be, so at first we have some sentence, some text file. We need to split it into some basic parts, which then will be processed. There are several possibilities: character-based tokenization, where we split the text into separate symbols; word-based, for example, here, like we see NLP is a fun. We split this sentence into 3 parts. But this approach has some drawbacks because, for example, when errors occur in the sentence, so and also it should have the size which could be even possibly unlimitedly large if you use word-based approach to tokenization. But if you use sub-word-based approach, this is the most popular now, for example, used in BERT, GPT, etc. So, for example, like in this case, we split unbelievable into unbelievable, yes, which could be also quite typical tokens, quite typical parts for other words. Or, for example, playing, we subtract from playing the in suffix, and so it's divided into 2 parts, into 2 tokens. So initially we have to split our text into these tokens. What is next? Next is a crucial stage for modern large language models. It's vectorization. Each token should be mapped into some vector. Vector. Usually these vectors are quite large, maybe several hundred or even thousands of components. So we are trying to map each word into some vector in high dimensional space. And such vectorization methods, such as word-vec, for example, they are so smart that, for example, here a typical example is given. The difference between vectors king and man is approximately the same as queen and woman. I will show it on this diagram. Okay, we have vectors here. For simplicity, they are depicted in 2 dimensions, but basically, of course, they have to be have much more dimension. But the idea is the same. If I want to calculate vector queen, yes, or I can subtract a man vector from king vector and add vector woman. So, and approximately, I get with high efficiency, I have the vector queen. Yes, there are some measures to assess what is the closeness of resulting vector to vector queen, but I experimented with some, maybe in some other video I will show how real closeness is achieved. Or, for example, vectors mathematics and statistics, they belong to the same area of knowledge approximately, and they should be quite collinear, as well as, for example, different from the pair of tiger and lion, which belong to animals group. So, yes, this is a real art to compute such vectors which correspond to each word. Basically, I will just mention the idea that the vector for each word, for example, in this case, for a word moon, for a token moon, is calculated based on with which words it often occurs close to. So, for example, if moon is close to cold, like here night, light, crescent moon, seasons of the moon. So all this word connection of the word moon with different words creates its vector. And it's calculated by quite, this vector itself is then calculated by very interesting mathematical procedures, for example, like in word-to-vec using skip-gram architecture. Then a two-layer neural network is used, and the coordinates after the network is properly trained, the coordinates of vector corresponding to each word are the coefficients weights of the hidden layer of this network. So very beautiful idea. And so these vectors can be really interestingly calculated. And for example, when then in the process of real work, I have some word vector for the ants, and then I want to find how, I want to calculate probability that this vector, how in real text can it be close to the word car. So I just calculate scalar product, dot product of word vector for ants with the weights for word car, and then I apply softmax package, and I have corresponding probability. Okay. So this was vectorization. So each token, once we have splitted our sentence into some parts, we calculate vector vector. We map each token we map into a vector. Now context encoding. So each token is mapped into vector independently. Now they should interchange the context. The tokens or words in the sense they should interchange to better understand the context. And for this purpose, a very nice mechanism used called attention is used. I will say a few words about it a little later. And for example, I have sentence: I went to the river bank. Yes, and I went to the bank to deposit money. Okay, of course, it's obvious that these two banks are different. One is a river bank, another is financial institution. And initially, the vectors for both these banks are equal. But some technologies about which I will speak now, they allow to change the coordinates of the vector depending on the context. And for this purpose, attention mechanism, which is used in transformer neural network, is used. Attention mechanism was not originally, but it was published finally after the decade of efforts by many scientists in the famous now paper "Attention is All You Need" in 2017. So this attention mechanism replaced very successfully long short-term networks and recurrent neural networks. So what is the idea? For example, we have a sentence: the cat sat on a mat. Okay, we have initial vector, let's say zero level context for word cat. But when it is it takes into account that the words met, yes, and sat are near it, we can have much richer context for analyzing this particular sentence. Mathematically, it looks like once we have some token in a sentence, it let us say sends a queries to each word which also is situated in this sentence. These queries are depicted here by the matrix Q. And then each token in the sentence has its matrix K, and by calculating dot product K, which is a key. And so our this word cat, it gives some query, some question, which words here are related to me. And comparing with the keys, we can actually calculate the closeness in some sense of different words or different tokens inside the sentence. And then using this dot product of Q and K, normalizing it by the dimension of the vectors, and applying softmax function, which produces as probabilities, and then multiplying it at initial values of the vector, we have the enriched vector, a vector for a given token, which now includes the context context of this token inside the particular sentence. So this quite simple mathematical procedure allows to calculate this value of attention. Also, what is important? Positional encoding, because each token in this way in the sentence is processed independently. So the word order inside the sentence is lost. So for this place, for this purpose, to each word, to each our vector, to each vector corresponding to each word, we add in simple additive way some positional information which includes information about the position of a given word inside the sentence. So in this way obtained vector is fed into the transformer network. Which is a transformer network? It consists of several layers, which in turn includes multi-head attention. Attention, we have already considered attention function. Multi-head attention means that we have different these matrices K and Q, which are shown in the previous slide, to capture different aspects of sense interaction between different tokens. Also, we have some residual connections, layer normalization, and following the attention part in each transformer is simple feed-forward neural network. About more information about the feed-forward neural networks and other neural networks, you can refer to other videos, our videos in our playlist. So in this way, in this layered structure corresponds to transformer. So again, it's a combination of attention functions and feed-forward neural networks. Each transformer network has two parts: encoder, where we take into information and extract its meaning, encode, let us say, in an efficient way, deep inner meaning, if there is some from particular text, and decoder extracts text from this information. This idea, for example, is used in machine translation. For example, we have a sentence in English, the red house. So encoder uses this transformer architecture. It extracts context vector for this sentence, not for particular token. In this slide, we have a vector for the whole sentence. So we have some context vector. It's fed onto the decoder, and decoder, which is trained to reproduce from the deep inner meaning the Italian phrases. So it translates as a result the red house into the La Casa Rossa, into Italian language. So again, encoder transforms the entire input into a context vector, and decoder decodes the output from the context vector. So, but for example, in text generation like ChatGPT, different Gemini, different chatbots, sometimes it occurs that encoder parts is not necessary. So we just have input, and we use just one part, left part of this transformer network, just decoder, and just decoder can be used. Decoder itself can be used just to generate next new word. After generating next word, it generates again for the extended sentence new word, and so the text is generated using transformer decoder model without encoder. But for machine translation, as we said before, encoder is certainly needed. So short conclusion: why transformers work well for natural language processing? Because it provides parallel processing, unlike recurrent neural networks, for example. All tokens are processed simultaneously, and we have a possibility to perform faster training of our networks. So transformers, due to the attention mechanism, of course, they catch long-range dependencies between words. So transformer can, or attention mechanism, it can efficiently include the connection between the words which are separated by many other intermediate words. But in opposed to it, the recurrent neural networks did not have such possibilities. So flexible context, multi-head attention, which we mentioned, considers different types of relationships at once, and positional coding can effectively be combined with attention. Yes, we said that we add positional information to our vectors corresponding to tokens, and then they're fed to transponder. Excuse me, to transformer network. So transformers, they combine speed, flexibilities, and long-range understanding, and they really make now the state of the art in natural language processing. Let's say a few words at the end how ChatGPT works. It's a large language model, which is, this abbreviation stands for generative. It's used to generate text. Pre-trained, it's preliminary trained. Transformer, it uses transformer network, which we have just said. So it has a layered structure. Yes, LLM in this case has a layered structure, some layers. In each layer, we have a mechanism of attention, or so-called self-attention, and feed-forward neural network, just as we shown in previously in diagram. So what are the parameters of this LLM? When we talk about feed-forward neural network part, of course, we have weights and biases. Yes, we know how each neuron of feed-forward neural network works. It should have a set of weights and bias, several weights and one bias for each neuron. Of course, some activation function, it should be a ReLU function, or sigmoid function should be also preliminarily defined, which will be used. So it constitutes about 70% of the parameters of large language model used, for example, in GPT-4. And also to calculate attention vectors, transformed attention variables, attention vectors, we need matrices which are used for the corresponding transformation of queries, keys, and values. They constitute, such the parameters, these matrices constitute about 30% of parameters. Of course, interesting. What is the total amount of parameters used in GPT? In GPT-2, there were 1.5 billion of parameters, constituting 12 layers of transformer network. In GPT-3, 175 billion of parameters. 1.8 trillion of parameters already in GPT-4 and the GPT-5, and about 120 layers of transformer inside transformer network. And for GPT-5, this information was not yet released. So about up to several trillion of parameters in GPT-4 and GPT-5. So when GPT answers the question Lionel Messi plays which kind of sport, or what will the next word we need to define, this information that Lionel Messi plays football is not explicitly stored inside ChatGPT, inside a large language model. So it's not like database. No. Due to vast training, however, these models make connections between different words. It also imbibe the semantics, the logic, the structure, the nature of each particular language. In this way, it can predict the next word with some probability. For example, he plays football with 46%, or preposition for 22%, or as 12%, etc. And corresponding to the temperature of our algorithm, a proper word is selected. So the fact that Lionel Messi plays football, it's not stored explicitly inside ChatGPT, but rather it is smeared, or it's encoded across 2 trillions of its parameters. So each parameter of 2 trillion parameters in some little insignificant manner contains part of the information which can help us to answer each particular question that we have. So thank you very much for your kind attention. This was a short overview of natural language processing, of its basic blocks, and also its application to the chatbots like ChatGPT.